if you've ever wanted to measure the speed of light yourself, well, this video is the thing to watch. Now, I should point out it's actually the second Let's Measure the Speed of Light video that I did. The one that I did about a week ago is up, and it's actually carrying out the experiment, and if you haven't seen it, you should probably watch it before you watch this video. This video is how to recreate that experiment and other ways you could do it and ways you might consider improving it, and at the end a challenge for you to do exactly that and hopefully send in some photos of what you've done and the results. So if you don't want to see a DIY video, don't look at this video. If you're still watching, well, what we're going to do is we'll very quickly go over the general nature of the experiment again, and then look at each of the components from the light emitter to the detector and so forth to give you some hints as to how you might be able to do it yourself. So up here is a list of things we're going to cover. The first thing is a very quick review of what this experiment is, and it's really quite simple, at least in form of a concept. We're going to generate a pulse of light, and we're going to send that pulse of light to a mirror at some distance away, and then that mirror will reflect the pulse of light back, and we will detect that somehow and measure how long it took between when we sent it and when we received it back. And if we know how long that was and what our distance was, well, it's fairly easy to calculate the speed. That's the idea. So the first thing we should look at is how we're going to sense that pulse of light coming back. The pulse detector that I used consisted of a reverse biased photodiode in series with a 1K ohm resistor, all powered by a conventional 9-volt battery. And in fact, just all soldered together. I was sloppy enough to not even use a connector for the battery, and the reason I didn't was the photodiode pulls such low current, it is a reverse bias diode after all, that really the thing that's going to spell the end of the battery is really the normal lifespan of the battery, not really the current that's being used at all. Of course, if you were doing this properly, what you would do is attach everything to a clip-on connector for the battery. Now, I should point out what's really important is that you keep all the leads very short. And the reason you have to keep them short is the currents we're dealing with are absolutely minuscule, typically in the microamp type range when we're dealing with a pulse coming in. And because the currents are in the microamp range, the voltage that we're going to read across the 1K ohm resistor will be in the millivolt type range. And I sure discovered that if you have leads of any length attached, well, you start getting noise from all sorts of sources, because these days we have so many switching power supplies and other things just spewing out RF energy that it's really quite a mess. So what you can see here is that I've just soldered everything together, and I've attached scope probes essentially right across the resistor. Don't even try to run this thing from a power supply, just use a battery and it'll work quite well. Now, I should point out a few things about the photodetector diode that we're using. The one that I chose costs about $2, and it's rather nice because it is relatively fast, about 15 nanoseconds, meaning that's about how long it takes to turn on or turn off. And it has a relatively large sensitive area of about 8 square millimeters, which for a diode is pretty large. And that's important because with the type of light sources we're going to be using, we generally can't focus it down to anything much smaller than that. So if our detector is much smaller, well, we'll lose a significant amount of the light. Like most silicon photodiodes, the greatest sensitivity is in the red and infrared regions. That's just sort of the nature of the beast. But it is sensitive enough in the green regions that with the green laser we're going to use, it'll work quite nicely. It is worth pointing out that when you're attaching oscilloscope probes to the resistor to measure the voltage across the resistor, which in turn is equivalent to the current going through the resistor, which is the current going through the photodiode, which is equivalent to the amount of light hitting the photodiode, it is important that those scope probes have really low capacitance. And by really low, I mean they should be around 12 picofarad rated scope probes or better. And that usually means they're 10-to-1 probes, meaning they attenuate the incoming voltage by a factor of 10, and the payoff for that loss in voltage is the way they're designed. You end up with this fairly low capacitance. And that's important because we want to keep the response rate of those diodes high. If we have a 12 picofarad scope probe and the diode is rated at about 10 picofarads at 10 volts, well, we can do a rough calculation and say there are a few more picofarads from just about anything, the wires, what have you. Well, with 25 picofarads across about 1 k ohm, what that means is we have a response time of that part of the system of about 25 nanoseconds, and that's going to be good enough. As you'll see later on, if you have a scope probe that has a much higher capacitance, that will slow things down probably tremendously. Now, what about a better diode, you say? Well, I did some looking around, and for 25 bucks, you can get a diode that really has single nanosecond or better type responses. It's rated at about 1.5 gigahertz bandwidth, and it's actually meant for use with optical fibers, which is not surprising because that's where you typically need high-speed diodes to send vast amounts of data. Well, the problem with that is the active area on that is about 1/10 of a square millimeter. So the amount of light that you'd be getting is going to be a lot less unless you can really focus it down to a tiny point. And that's, of course, no problem when you're dealing with tiny things like optical fibers. But if you're trying to do what we're doing, it makes it kind of hard. The other thing is, even with that incredibly high response rate, the problem is now that everything else in the circuit is slower. I mean, I just talked about how the scope probes and stuff all bring the response time to the rest of the circuit down to somewhere in the 20-odd nanosecond range. So it probably is not going to be very helpful to go for a diode like that. The unfortunate thing is a lot of photodiodes on the various websites like DigiKey and Mauser and Newark don't all have the speed specs on them, because in a lot of cases you're not really worried about these incredibly fast response times. So it does take a bit of digging to find a good fast one, but I encourage you to scour through those and other sites to see if you can find a better diode than the one I found, and if you do, be sure to let me know, because I'll certainly put it up for everybody to see and potentially use. The pulse generator that I used was a laser diode, and it costs about 25 bucks, and it can spit out a maximum of about 20 milliwatts of optical power in the green light region. Now, the thing about 20 milliwatts is that's in the region where if you stare at it, you can certainly start doing damage to the eyes. And because of that, I tended to operate it pretty much at its lowest output power level, which was somewhere around 5 milliwatts, which worked quite well. And if you get one of those diodes, I would strongly encourage you to try and operate it at as low a power level as you possibly can. There is sort of a minimum power level, because below that there is not enough amplification going on in the chunk of silicon or whatever semiconductor they've used to actually sustain laser action. So you do need a certain amount of optical power going out at a bare minimum. And you can sort of tell when it's lasing because you start seeing the sort of sparkly laser type light in the light that's emitted. And if you have the current going through the diode just a little bit too low, well, it's not sparkly. It operates pretty much more like a conventional light emitting diode. The circuit is actually pretty simple. It's just a laser diode in series with a 1 ohm resistor, and the only reason for that 1 ohm resistor is so that I could hook up a scope probe to it and we could measure the current going through the diode. And that's because all of these things are generally rated in terms of maximum current, because with diodes, if you increase the voltage, it's an exponential type curve. Slight increases in voltages produce incredible increases in currents. So you really have to operate them more in a current control mode. And the easiest way to map power to input is to relate it to current. And so using that 1 ohm resistor and being able to measure the current, I was able to set my pulse current to around 50 milliamps. So the circuit, again, is very simple. It's just the diode in series with that 1 ohm resistor and attached to the output of one of these cheap signal generators. The signal generator is set up to produce a 100 nanosecond rectangular pulse 1,000,000 times a second. And I've adjusted the voltage on my generator to a 5 volt pulse with a 5 volt offset above zero. Now, it is worth pointing out that these cheap signal generators are not very good in terms of setting their output voltages. So in doing those settings, I ended up with an output voltage as seen on the diode of around 6 volts, as opposed to perhaps 5 plus 5 is 10. And doesn't really matter. That's good enough, and that's what worked. If you're using the same sort of signal generator, don't rely on my 5 volt and 5 volt numbers. Do some experimentation to make sure you get it right yourself, and just gradually turn up the voltages until you start seeing the diode do some laser action. Oh, and one more thing, as Lieutenant Columbo would say. When you're setting the offsets, the reason for doing that is you don't want a large negative voltage going across the laser diode, because it's not built to be a rectifying diode and its maximum reverse voltage is pretty low. Now, I should point out that if you do look at the current going through the diode, what you will see is some very big pulses at the turn on and turn off sections of the pulse. And that's because the diode looks like a gigantic capacitor in many ways. And so what you're essentially doing when you're putting that spike in is charging up the capacitor or discharging it. We should at this point talk about laser safety. And to talk about laser safety, well, here's my cool red glasses. The neat thing is you can get laser safety glasses fairly cheaply on any of the online places, because it turns out people are using lasers for things like hair removal. And so these glasses cost me about 15 bucks Canadian, so that would be 10 bucks US or so. It is important that you check the wavelengths of the glasses you're buying, and not all those sites list them properly, but you know, this is red, and it actually specifically lists what wavelengths of light it blocks, and it does block the green of the laser that I'm using. In fact, so much so that if I put the glasses on, I can't see any sign of the laser light at all. And why is that important, you might ask? Well, it's because laser light typically can get focused down by the lens in your eye or any other lens to a minuscule point, concentrating all the laser energy to that point and pretty much burning anything at that point. And that can happen to the insides of your eye and potentially do permanent damage. And that, by the way, applies to just about any laser anyway. So it's really a good idea to use glasses if you're walking around and there are laser beams flying around. Now, it's not just the laser beam that we're worried about. but it's something called glints, and that is when the laser beam hits something that's shiny, maybe a screw or anything in its path, it will reflect from that. And if one of those reflections goes into your eye, there could be problems. When I was a grad student and we had a big giant laser, it ran off three-phase power and all of that, and it was green just like this one. And me and a buddy were working in the lab one day, and he suddenly said, "Close your eyes." And I did. And there was a green dot on my forehead, apparently. So he turned the laser off, and we figured out where that glint was coming from, and everything was fine. But that was a great example how, well, if you didn't have somebody watching out for you, or didn't have some goggles like this on, well, you could be in big trouble. So the bottom line is, for 15 bucks, be sure to get some glasses if you're dealing with lasers, or keep the powers so low that it's really not going to be a problem. And I strongly encourage you, before you do anything, to go to the various laser safety websites and read up on lasers and what the safe power levels are and how to be safe with them, because that's really something more than I can cover very quickly in a video like this. So now that I've scared you with lasers, there are other ways we could send a pulse. And one thing I did was I also bought a couple of light emitting diodes, and I tried one of them, and well, it was a red diode, which was really good because that is the more sensitive region of our photo detector. The unfortunate thing is its speed is considerably slower than the laser, about 30 nanoseconds or so, and its power level is also lower at a maximum of about 3 milliwatts. And well, as you can see, you can sort of see the bump on the oscilloscope screen, but only barely. The reason the pulse is so low is not just because of the lower power level of the diode. It's also because that diode has a built-in lens to produce a somewhat parallel beam coming out of the diode. And that would be very nice for many applications. But for us, what essentially it does is it magnifies the diode chip way at the bottom of that package. So when we use our magnifying glass to focus the beam, we're essentially seeing a much larger area emitter. So when we're trying to focus our beam to the other end of the basement and back, well, the total light area that is produced is way bigger than we got with the much smaller emitting area of the laser. So that's a problem with that diode. Now, what I would encourage you to do is see if you can find a better diode that does not have a lens in front of it the way this one does. And again, the problem is very few of the LED diodes have any specs regarding speed. So you could try a lot of them, would be one way of doing it. The other thing that might be interesting is one could potentially put another lens in front of the lens of this diode. That would probably work out a bit better, but it makes things more complicated. You could also try hacking the lens away from that diode. That would probably expose the diode itself to the air and probably cause degradation of the diode itself over time. So none of those things are great solutions, but was really kind of cool was the fact that, well, you could sort of see it with the diode. Now, the one thing that I did have to do was to be able to bump up the size of the pulse so we could see it. I had to swap in a higher capacitance probe that didn't do the 10-to-1 voltage attenuation of the low capacitance oscilloscope probes. And I think in doing so, well, take a look. You can certainly see how it rounded the pulses quite a bit. So there's probably some rounding of the pulses from the fact that the emitter diode is much slower than the laser. And then we're using a probe that slows down our detection circuit. Well, you get those great big bumps. But I'm optimistic that with a little bit of work, you could probably get that to work much better, maybe with a better diode. And it would be wonderful if somebody did that and told us how, because you could do the whole experiment with something like a LED diode, and at that point not have to worry about laser safety at all. There are other ways that you could consider making those pulses of light, and one of them is to use a xenon strobe of some kind. And this one here is something that I picked up after Halloween at, I think, one of the hardware stores when they were selling them off to get rid of them, and I think it cost me something like $10. And it produces a pulse of about 50 microseconds, which is not bad. And so there's another way you could do it. Now, with a pulse that long, you would have to do things over much greater distances, so you'd probably have to focus it with a big lens and have some sort of a reflecting mirror miles away. And, well, it would not be quite easy, but there's certainly perhaps something in there for someone to experiment with. The most intriguing thing I came across were these laser distance measurers, and I tried a few. Here's one from Canadian Tire, which is a very iconic Canadian hardware store, and this is their store brand. And when you turn it on, it produces a whole bunch of pulses at a rate of about, I think it's 30 megahertz, meaning 30 million pulses a second. And those pulses seem to have a upwards type time constant of maybe 20 nanoseconds or so, and maybe a downgoing time constant of 50 nanoseconds. And I suspect the time constants we're seeing are in fact the time constants of our detector diode, as opposed to the time constants of however that laser distance measurer is modulating the output laser beam. So I think those things could be used to make a really great version of this experiment. But the unfortunate thing is I tried a different one, and the different one produces pulses, but, well, a lot less regularly and not nicely shaped. And, well, it just didn't seem to be usable. So I think what would be great is if anybody who happens to have one of those things and is interested in trying the experiment, try putting together the detector as I've described here, and shine your laser distance measuring tool or rangefinder at it and see what type of pulses it generates and whether they're usable. In the case of this one, it seems to produce about 16 pulses, about 300 odd nanoseconds apart, and then it misses a pulse and then repeats. And that missing pulse could be quite useful if you're trying to measure over longer distances, where you might start getting, in fact, pulses overlapping because your mirror is more than 300 nanoseconds in distance away from your transmitter receiver setup. If you want to do it in a way that's much more like the way Photo did in the 1850s, using a mechanical device to chop your light beam from whatever source, well, perhaps the way to start might be to take a Dremel, which can go up to about 35,000 RPM apparently, and put a tool at the end that has some holes in it. And I found various cutter blades that were listed as diamond cutter blades tend to be made out of metal, and for some reason have 8 circular holes in them, and they could be used to chop a laser or other light beam. Now, unfortunately, when you do the calculation, the time between those holes when they're spinning at 35,000 RPM is around 21,000 nanoseconds. So to be able to do something with that, you'd probably need distances that are much more comparable to the distances that Photo used way back then. In other words, many kilometers or miles away. Optics and mounts. And here's where I really got into the do-it-yourself mode. You could certainly run out and buy thousands of dollars worth of optics that you might find in an optics lab. And if you wonder what an optics lab in a university looks at, well, take a look at this photo from The Big Bang Theory. That's Leonard's lab, And what he has there is a very standard optics bench. In fact, you can even see in the corner it says Newport, which is the standard supplier of those benches. And when I saw that episode years ago, well, it really brought back memories to me, because that optics lab is the splitting image of the lab that I worked in when I was a grad student. So if you've ever wondered whether the stuff that they show you in the labs in the Big Bang Theory is authentic, it is very authentic. Anyway, we don't want to spend 10,000 bucks on a table like that, or whatever they cost these days. And quite truthfully, using expensive equipment like that tends to obscure things. So, well, as you can see, I cobbled together things, and I found that perhaps the cheapest way to mount things is to use old photo tripods, or if you don't have old ones, you can certainly get them real cheap online. And the mounts between the tripod and whatever device we're using, the mirror, the sensor and stuff, is a standard Manfrotto type mount. They're called 323 quick release clamps, and they fit onto the Manfrotto 2000 PL-14 plates. And you can typically get these things online for something like $5 for the pair of them. And it just makes things so easy, because you can put your plate on whatever device you're trying to mount and then clip it down onto your tripod. And if the tripod has a decent head, adjust the position. So that's a very cheap and effective way of making optical mounts. The magnifying glasses, well, what can I say? They were the cheapest ones I could find at the local dollar store, and I just used some electrical type clamps or cable straps to attach the magnifying glass to the end of a 2x4, which in turn was attached to the Manfrotto tripod plate. And if you don't have any bits of wood to use for these things, or cable or pipe clamps to attach the magnifying glasses, well, maybe talk to your neighbors or something, because anybody who does any home woodworking or other DIY type stuff will inevitably have a box full of things like that, and it's kind of fun to do it using leftover stuff. The oscilloscope and the signal generator. Well, the signal generator that I used is this cheap one, as I've pointed out numerous times, and ones like that show up at all the various online sites all the time under a variety of different names and numbers, but they generally all look alike, so I suspect they're all coming from the same factory. I think mine was a JDS one. Other people have bought ones that are called Cooltron or something like that. It probably really doesn't matter. It is worth noting they come in different speeds, and it's not always clear on the ad which speed you're buying. I have the 60 megahertz one. Probably isn't too critical for the square pulses we're using, but it also turns out that the slower ones really aren't generally that much cheaper. So if you're going to buy one, go for the 60 megahertz version, or look online, see if you can get any sort of a signal generator that can produce the type of pulses we need, namely 100 nanosecond. Doesn't really matter how often they repeat, whether it's a million times a second or 100,000 or 10 million. It's really more the pulse width that's critical, and the maximum voltage of that pulse, which needs to be around 6 volts to be able to run the laser. For oscilloscopes, what I would suggest is a good old-fashioned oscilloscope. And if you don't have one lying around, you can often find them online for about $50 or something like that. Now, you do want one that's reasonably fast, and I would suggest something like a 50 megahertz scope or better, although probably a 30 or 25 megahertz scope would be fine too. The nice thing about the old analog ones is, well, they're just a bit simpler than the digital ones, and one can imagine that the oscilloscope beam is indeed sweeping across the CRT as the light is traveling down to the mirror and back, and well, there it draws that pulse right there, as opposed to everything being digitized and stored and who knows what else. So I rather favor the old scopes for this sort of experiment, and it's a good way of keeping things rather inexpensive. You do, of course, need or should have a low capacitance probe. As I said, mine were 12 picofarads. That's moderately low. Generally, you can get a 6 picofarad type probe for in the neighborhood of $50, so they're not very expensive. And you only really need it for the detector probe, so you only really need one of them. So if you have an old scope that has slow probes, you only need to spend $50 more to get a faster one. I did a quick estimate of what it would cost. Well, I'm going to say you can get a signal generator for $125, a used oscilloscope, $50, the laser or LED diode and a photo diode, well, probably a maximum of $25. Tripods, well, I've sort of said get them used or get them online. I looked online. You can get new, not the greatest, but good enough tripods for $20 a piece. But see if you can get some used ones. If you can get a used Manfrotto, I mean, you can't do much better than that. The tripod plates and holders, again, look online. You typically can get the pair for about $5 each. And, you know, the miscellaneous bits and pieces, the magnifying glasses, the 2x4s, the screws, what have you, I've put down $25. So for a grand total, you could put together the whole thing for about $300. But if you're looking at this video, chances are you have some of this stuff lying around, and you can probably do it for a lot less. So here's the challenge, and I've divided the challenge into a number of separate challenges. The first one is, can you do this experiment in a cheaper, simpler, or more obvious way than the way I've done it? And the whole idea with this experiment is to really demonstrate the speed of light and make it obvious as opposed to hidden behind gobs of equipment or gobs of calculations. So that's the first part of the challenge. Second part of the challenge is, can you do this experiment in a safer way? And by safer, I mean without using the laser diode. So if you can find a better LED than the one that I used, that is perhaps a bit brighter, a bit faster, and maybe doesn't have that lens in front of it so that it can be focused better and can pretty much stand in for the laser and get almost as good a result as we got with the laser, well, that would be fantastic. And if you try some diodes and you find one that's good, please let me know, and I'll certainly post it somewhere online. Third part of the challenge, laser measuring devices. If you have one of those things, build the detector and try the experiment with the laser measuring device. And, well, if you're lucky, you'll have one that produces a suitable series of laser pulses. And if it does, please let me know, and I'll tell people what make and model of a device you're using so they can find it. I would be thrilled to hear from anybody who's repeated this experiment and what speeds of light they've gotten. And I'll try and compile a list of all the different experiments that were done and their values. And who knows, if we average them all up, maybe we'll get a pretty good number. So that would be a really neat thing to do. And finally, I will try and maintain a list of the best parts to use for this experiment based on what I've done and based on what you send me, so that anybody repeating it can, well, do it without the need for all the experimentation that I've done, and hopefully some of you are going to do. So that should be quite a bit of fun. If you're still watching this video, I congratulate you, and I hope you found it useful. And don't hesitate to put questions or comments or thoughts or ideas in the comments below, and see you next time.